So let me say something about the last homework. I hope it's a fun one. It should be a fun one. All right, we're starting out. So it's pretty short, but it's fun, and I want to actually give you a theorem that answers one of these immediately today. So the first question, the first question is sort of the one that's harder, I think, and I've been promising this sort of for a while. You all, I think, have already done this for the quasi-local case, but show if R is semi-quasi-local, that is, has only finitely many ideals, then every invertible ideal of R is principal, right? So we know this is true for the quasi-local case, where you've got only one maximal ideal. This is also true if you've only got finitely many. This one's a little bit more subtle and delicate to play around with. This one's sort of the one that's will require a little bit more work, in my estimation. And number two, I want to consider the ring of algebraic integers z adjoined with the square root of -89. This is, in fact, the full ring of integers. It's a ring of integers, so it's Dedekind, and it has all that nice business about there's an ideal, prime ideal in every class, and class group is finite. And in fact, I'll tell you what the class group is. It is in fact cyclic of order 12. You need a little bit of number theory to be able to do that. It's not too hard, but I'll just give it to you here. A should be an easy answer. Two questions really in A. What is the elasticity of this domain? Well, you don't know how to answer that yet, but I'm fixing to give you a theorem that will make this immediate. And what is the norm of an element of, what is the norm of a typical element in this ring? Number B, show that there is no irreducible element in Z adjoined with the square root of -89 that is of the norm 3 to the kth power for k between 1 and 6, with the exception of the elements plus or minus 3. It turns out, so you need to show that those are irreducible. They have norm 9 actually, but those are the only irreducibles of norm 3 to k for those powers. And finally, the elasticity is actually attained by an element in here. I hope you find the same one I do. But in part B, I might sort of give you a hint where to look. Find an element in C square root of 89 that has elasticity, so it's got maximum elasticity. All right, so that should be fun. I had to whip out my calculator this morning, but if you do, if you think about this from modular arithmetic, you can eliminate the cases to help you out here. So anyway, hopefully that'll be a lot of fun. And any questions, let me know. And now I'm going to follow up on what Jared did. And this will actually answer one of these least questions for you immediately. So let me give you a theorem. You don't prove it. Well, let's recall first. Hang on. So I'm going to define first the elasticity. So Jared, I watched his lecture. He talked to you a little bit about elasticity. Well, we've got this thing called the elasticity of the element. Well, what is this? This is the supremum where each alpha I by J is, well, R, here it is. So you take your element and think of it this way, factor it as many ways as you can, and the irreducibles, let's assume we can factor it into irreducibles in the first place, otherwise I'm in big trouble. So it's something that actually can be factored into irreducibles. Look at every factorization into irreducibles that you can, and just make a list, right, of the number of factors that you see, right? Now look at all quotients of this and take the supreme, right? So for example, if X is a prime element, the elasticity is one, right? Because there's only here. In fact, I can take that a step further. If X is a product of primes, then its elasticity is one because all factorizations are the same way. Everybody okay with that? Yes.
I have a question. We can find this elasticity notion in domains that are not atomic.
Sure, because you can talk about a single element here,
Okay.
right? You could and so what you can do, you can just look at this now. Generally speaking, if R is atomic, you can find a row of R to be the supremum over all non-zero non-units. You could do this more generally by talking about the supremum over non-zero non-units that are atomic, right? So in a certain sense, what the elasticity of an element, and more on a bigger global scale, the elasticity of the ring. The elasticity of the ring measures how badly the atomic factors could be, right? So for example, if it's atomic and not necessarily, it's not necessarily a factor. Oh, maybe I misunderstood. What did you say? Oh, I did misunderstand.
Okay.
Yes. Because essentially what that means is that all factorizations have the same length. Notice that if R is a UFD, then you have elasticity one, but the converse isn't true because there are half factorial domains that are not, factorial. Right? Now, here is, of course, let me give you this example. This is one of my favorite ones. This is an HFT. I believe that Jared went over this, right? When you have these kind of constructions where you have a small field plus larger field, X power X or X single bracket X, these things are HFTs, right? And in fact, they're UFDs if and only if the two fields you use are the same, right?
Oh, these are the O M plus D construction?
Yeah, so if you have, bigger fields, then the construction. These are always HFTs. And I'll give you an idea. Did Jared do that through? I thought he did some constructions like this.
Yeah.
Okay, well, in general, this always works. And they're UFDs if and only if K equals F. Certainly if K equals F, they're UFDs. Everybody agree with that? The other implication is also easy because if there exists alpha in F, but not K, then alpha X over X, alpha is in quotient field. Right? Everybody agree with that? So if there's an alpha that lives in F but not in K, then it's in the quotient field of this ring, right? And so if K is strictly contained in F, then R is not completely interclosed. So not UFD. Because all UFD are completely interclosed. Right? So this is kind of a nice little thing. These constructions are always HFDs and they're only UFDs if the two fields are the same. And if you look at this, I love this example because if you take an arbitrary element, actually, it turns out that an element in here, Jared probably went through this, an element here is a unit if and only if the constant term of the power series is not zero. And it's an irreducible if and only if the ORD is one, right? That is, it's got a non-zero, it's got a zero constant term and a non-zero X term, right? So if you look at X squared, so X squared factors this way, X times X, or for example, 1/pi x times pi x, et cetera, et cetera. So in fact, the element X squared, all its factorizations are linked to, but there's uncountably many of them.
No, I was about to ask if these just only have one atom and every other atom is associated, but no, right? Because
Right.
we can have constants that I'm not right.
Yeah, there's uncountably many atoms. And it's almost a cheat, isn't it? Because if you pass to the complete integral closure of this, they're all associated. But here, they're separated out, right? This is why units, sort of hidden units, are so important to factorization, because we have these kind of trivial things here that become non-trivial in this smaller range. Okay, everybody okay with elasticity? So let me give you, this kind of ties together the stuff that Jared talked about last time. And all this business we've been spending time with, I talked about Dedekind domains, and I talked about, oh, look at these sexy things that have like, rings of algebraic integers. They've got a finite class group. They've got a prime ideal in every class. Here is a really cool result. And this has as far as I can put together, rather interesting. Let R be a ring of algebraic integers. And and let me call the class root of R, the ideal class. Then the elasticity of R is given by the following cool formula. The Davenport constant of G divided by 2. If the order of G is bigger than 1 and 1, where, let me make clear, D of G is Davenport constant. This is a really neato theorem, right? By the way, here's another theorem. This will help you on that too. That's not fair. I knew you did that.
No, no, you're toast, you're toast.
Jared told, okay, I want to make sure. Okay.
I'm not that.
What? So, did he prove this for you last time?
No.
If a group is cyclic order n, then the Davenport constant. Anybody know how to prove it? So, all right, I'll give you a sketch of the proof there. No. In this group, if you have one bar to itself n times you have 0 bars. So 1, 1, 1, and of these is a 0 sequence. All right, is it clear to you all that there's no subsequence of this? It's going to sum to 0 because the order of 1 is exactly. So I've given you a 0 sequence of length n. So all right. So that means that for a cyclic group, the Davenport constant has to be at least the order of the group. All right. Here's something where I don't need cyclic, right? In fact, what I'm going to prove for you now, did Jared prove that the Davenport constant always less than or equal to the order of the group? Well, we'll do that. I should have structured this in general better, but I didn't. No. Davenport constant for G is always less than or equal to the order of G. This don't need cyclic here. I clearly needed, well, it seems that I needed cyclic to do this because I picked this element here that generated group. Well, pick n elements in G. Arbitrary. In fact, I could have picked the same one n times however life. Now, consider the following. Uh, so just look at these kind of in tandem. Let me point out that if sum yi is equal to 0, then the sequence x1, xn has 0 subsequence. And we're done. Because remember, what I'm trying to prove is I want to prove that any collection of n things has a 0 subsequence, right? Everybody okay so far? If not, then pigeonhole says yi equals yj. Why is this? Because notice every one of these elements is in G, right? None of them are the identity. And none of them are the identity. That must mean two of them are the same, right? Now let's say that I is strictly less than j without loss of generality. And so what we have is x1 up to xi equals x1 up to xi plus 1 xj. And so 0 so again, x1 up to xn has 0 subsequence. Therefore, and that's what we needed to show. So in general, for any group, the order of the group, Davenport constant is no more than the order of the group. For a cyclic group, we see that we have equality. Right? And in fact, that's an if and only if. That is to say, a group, this is a little bit less easy to see, but it's not too difficult either. A group is cyclic if and only if the order of the group is Davenport constant. This makes one of the problems on the homework pretty easy. Okay, so let's get on to this. The theorem Valenza Narkiewicz. And along with this comes some mathematical advice, I guess. Proof. Uh, This theorem is, I hate writing that, but I'm gonna do it anyway. If the order of the class group is one, this is clear, right? Because if the order of G is one, that means that R is UFD, and that means that, the elasticity is one, right? In fact, UFD is stronger, a stronger condition than one. And I'll give you a corollary when this is done. So here in my proof, I'm going to assume that the order of, the group is, n bigger than one. So let, what's this one? Oh, and, there we go, that's what I meant to do. I don't want it to be the order of the group, I want it to be the order of the Davenport constant. There we go.
So
So-
it's true that Davenport constant is one, if only if slice and group is one.
Yeah, that is actually a theorem. So, let's let n be the, order of the Davenport constant, or the Davenport constant. What is the Davenport constant? That is the length of the longest zero sequence that contains no proper zero subsequence. Everybody okay with that? So what this means is, of course, maximum here means it's got no zero subsequence. Of course, its length is n, which is the Davenport constant. This means, so interpretation, I1, I2, In is principal. So if you take this ideal as principal, but no proper subproduct, I agree with that. So what I want to do is I want to pick the following, I want to pick primes of the following fashion. I pick a prime ideal for every one of these ideal classes here. I pick a representative prime ideal in it, right? This is part of what I know I can do for rings of algebraic integers, because every ideal class contains, in fact, infinitely many, but all I need here is one prime ideal in every class. Now two, and of course, every one of these ideal classes has an inverse. It's the class of I2 inverse. Or you might, if you write it in the additive notation, let's say minus. There's a prime in those two, right? So I pick prime there. Notice if there's overlapping classes, it doesn't matter because I can just use the same prime over again. Right? Now, check this out. The product P1, P2 up to Pn is principal and it's generated by alpha. And the product Q1, Q2, Qn is generated by beta. Notice that, of course, if you replace all the i's with their inverse classes, that also gives you a maximal zero sequence of intent as well, right? Now, I claim that alpha and beta are irreducible. Anybody see why this is the case?
There's no proper subproduct of this principle.
That is correct. Let's suppose, just for giggles, that alpha is equal to xy. All right, so I can break alpha down into small. Now, the ideal, we don't have unique factorization of elements. We do have unique factorization of ideals. So some product of P1 of Pn is right. So maybe the first K of these is X and then the rest of them are Y, right? It has to be this way because X and Y both have prime ideal factorizations. And this is it. It has to be a subproduct of these. Again, unique factorization of prime ideals is nice. Everybody okay with that? But no subproduct is principal. So without loss of generality, Y is the empty product. Primes. So Y is a unit. Therefore, alpha is irreducible, right? Everybody okay with that? It's clear the same proof works for beta as well, right? So alpha and beta are irreducible. And it's precisely because of the Davenport constant thing. It's amazing how this subproduct comes up because basically alpha and beta, these are the sort of the largest, this is like building a very large atom out of lots of nuclei or whatever. It can't be broken up any further, right? And this is big. You can also make this small. Right, because each EI, QI is principal. By the way, we select them, right? P1 is in the, or Q1's in the inverse class. P1 is, right?
I can imagine that the same argument works and these gammas are also irreducible.
Right, it's in fact easier here, right? Because notice that we've got these huge irreducibles in a certain sense. They're very fat with prime ideal factors here. And here these are actually sort of the smallest irreducibles. So only the product of two non-principal primes, right? each gamma I is irreducible by the same argument that we gave over here, only it's easier. Right? So there exists U in the units such that U alpha beta is gamma 1, gamma 2, gamma n. And if we call this element X, then rho of X is greater than or equal, right, because I might have been able to find some other factorization. Therefore, actually, that's the easier part of the theorem. And this is a very, so this theorem actually first came out, Valenza did the other direction. And in fact, I don't want to scare you all about this, but one of the funniest things about that paper, it appeared in the Journal of Number Theory in 1990. And at the bottom, it said, received by the editors, October 12th, 1980. So 10 years of publication, not so shabby, right? Of course, I shouldn't blame the journal. I'm gonna lay off of that because that could have been the journal's fault, or it could have been the author's fault, or it could have been the publisher's fault. Who knows? Valenza did one direction of this. What I just did was go to Narkiewicz like a couple of years later. And it's actually kind of easy. So always sort of, Valenza actually, I think, did the heavy lifting because I think the other direction is a more interesting direction, but always make sure you sweep up. Okay, so let's look at the other direction here. So what we've shown so far is we have okay, that's what we've done so far. We need to get the other direction out of this. And for the other direction, let's suppose, or for the other inequality, I should say. Suppose that we have this here, and let me make clear that I mean for these to be irreducible factorizations. Alpha I, beta j, irreducible, and none are prime. None are prime doesn't really affect anything because, for example, if alpha 1 is prime, that means up to associate it must be one of these, and so you just cancel them off and consider the lower factorization. Notice if everything is prime, then you've got elasticity 1, right? So what do we do with this? Well, if you look, let's factor each of these. So let alpha I be pi1, pi2 up to pi p sub I. And beta I.
The ideal generated by alpha I.
That's exactly right. Yeah, I'm being a little sloppy here. And beta I is Q I1, Q I2, Q S I. Like that. Oh, and one more assumption. I'll assume K is less than or equal to M, just for ease. So, of course, at random, these factorizations I might pick something the same length, but I'm going to assume that what's on the right is at least as long as what's on the left, otherwise I'll reverse them. So, if you factor this, then P 1, P 1, 2, P 1, T 1, P 2, 1, P 2, T 2, up to P K 1, P K T K is equal to Q 1, 1 to Q 1 S 1, Q 2, 1 up to Q 2 S 2, Q, what was it, M 1 up to Q M S M. So I have, this is basically, this is an elemental factorization. I put parentheses around this and consider this to be the ideal factorization. I do this. And in particular, what this gives me is the number of prime ideals on both sides have to be the same, because prime ideal factorization is the same. So in particular, the lengths have to be the same. So I get T1 plus T2 plus T K is equal to S1 plus S2 plus SM. So let me point out that this is less than or equal to MK. Where N is the Davenport constant, right? Because think, what is T1, for example? T1 is the number of prime ideal factors in alpha 1. And so T1 is bounded above by N, right? Because the most number of prime ideal factors that any irreducible can have is bounded by the Davenport constant. Anything larger than that forces it to be broken down further. So this is bounded above by N, and there's K of them. On the other hand, each one of these, you can also say there's at least two, because remember, none of these are prime. So the smallest you can go for each of these, say betas, is to have two prime ideal factors, right? It can't be one because we're assuming none of them are prime. So this is greater than or equal to M. So I get NK is greater than 2M. And so N over 2 is greater than or equal to M over K, which is greater than or equal to the row of X, whatever this element is. Therefore, N over 2 is greater than or equal to row R. Any questions on that? Yes.
This last part, sorry, I don't get it, how we obtain these bounds, NK and 2N.
Well, because what T1 is, so let me tell you what T1 is. Well, there's T1 of these things that make up this irreducible, right? The maximum length of a zero sequence, because remember, when you're looking at a product of prime ideals that is principal, it's a zero sequence. And so that means that the longest this can be is the length of the Davenport, or is the Davenport constant. That's the longest possible zero sequence that has no zero subsequence. Because if you have a zero subsequence, if this is principal, the other one has to be principal, and now you've broken that down, right? And the bound is similar here, because if you have beta 1, it's Q11, not the Q1 S1. There have to be at least two here, because I assume that these things are not prime, right? So if they're not prime, the irreducible has to be a product of at least one I'm sorry, at least two, non-principal ideals, giving this upper bound here. Lower bound. Okay, any questions on that? Is that clear? That's kind of slick, isn't it, right? And it shows you how the importance of the class group and this kind of counting stuff can come in. All right? All right, any questions? Any questions out there? All right, we will see you on Wednesday.